Right. Thanks. And yeah, thanks to the organizers for putting this together. Michael Hutchings, who I see is here today, for writing great talks for Joe and myself and Ipsita to copy. If you want to see this talk done well, maybe log off and go to YouTube. But if you want to see it done by me, well, stick around. So get going. So we can, by the way, when I've noticed with Zoom, whenever I'm sharing my screen, I have a hard time viewing the chat for some reason. So if questions in the chat and I don't respond to them, it's probably because I don't see them and not because I'm actively ignoring them. But let's recall the setup of last week. So we have a function on some manifold, which is S1 valued. And we want to think about like S1 valued Morse theory. And we have some metric G on it. So what we want to do is say, given a homotopy of data of this form, so F sub t, G sub t, we need to think about the bifurcation times where genericity fails. So this is a natural thing to do if you want to show, like, I guess Joe, his main motivation was showing that d squared is 0 for S1 valued Morse theory, but we want to think about things like invariance. And so that requires studying particular bifurcations. And I guess, you know, most of the bifurcations you're going to see would be familiar from R valued Morse theory. But since F t is S1 valued, one failure of genericity that we could have would be an index 0 flow line from a point to itself. Oops. So this is the sort of flow line which will be glued to itself, really not by me. So from a point to itself. So what that means is when we want to ask what sort of broke, we need to think about, well, we could glue this thing to itself a number of times. So we need to think about broken flow lines of the following form, where we have maybe a point P and a flow line connecting P to Q, call it U plus. And then we could have this flow line U0, and we could glue it to itself some arbitrary number of times. And we want to add, well, I say we could glue it, we could sort of concatenate here. We want to know whether this glues for the more generic times. So the idea is that some configuration like this shows up at this bifurcation time where genericity fails, and we want to know whether we can glue. So I'll actually write that down. If such a trajectory appears, at say t equals 0, we want to investigate whether it glues. So we want to look at glues on one side of, like for t very small and negative, or maybe it glues for t very small and positive, or maybe both. This is something we want to investigate today. So really that pitch is more Ipsita's problem than mine, because today we're just going to focus on the case k equals. So really we're not gluing a Morse flow line to itself just yet. That'll be the third iteration of the talk. So just for the sake of ease of notation, by ease of notation, I mean since I have a curve called u plus, I'm going to write u plus and u minus all the time, so I might as well make it look intentional now instead of calling my curve u naught. So we're going to have a point P, a flow line u plus down to Q, a flow line u minus down to R, where P has index I plus 1, Q has index I, and R also has index I. So in particular, this sort of analysis is perfectly valid for R-valued Morse theory. We don't actually need this flow line from a point to itself just yet. That'll be next week. So maybe it's worth seeing a picture of this actually happening. And it's sort of a harrowing picture because the example is that we've dropped our donut, which we hate to do. And so as we drop our donut and it sort of tumbles towards the floor, sure to land fudge side down, there's going to be some moment where it's just perfectly upright. And so have flow lines here in the middle, connecting points of the same index. We'll also have flow lines which is the way they're supposed to. So this would correspond to time equals 0 where genericity fails. And we want to know on either side of when we actually have the generic setup, how do these things glue? And so maybe what we'll see is on one side, flow line from index 2 to index 1 coming out of connecting these two, this broken flow line here glues to something here, but then it doesn't glue on the other side. So we'll return to this example at the end of the talk, and like once we've done our analysis, we can actually say how many of these broken flow lines. I guess there are 8 here, right? Because you have sort of 3 choices between 2. We'll see which of these broken flow lines appear on the left and which appear on the right. Okay. So let's just reestablish some notation from last week. Our flow lines are denoted u plus and minus. We've already got that. And a priori, or like when we start, you know, when you go to negative infinity is when you go to one of your limit points. When you go to positive infinity, you go to the other limit point. But what Joe did for us was translate these by choosing R very, very large and sort of redefining the notation of u plus and u minus. We said u plus is actually u plus of s minus r over 2, and u minus is u minus of s plus. This way, when s is near 0, u plus or minus of s is near q. So we'll have to worry about this soon enough. Cutoff functions so that we can pre-glue our curves. And I don't trust myself to draw the cutoff functions right now. So we have some prepared artwork. All right, so these cutoff functions are going to allow us to glue these 2 flow lines together. So we have some coordinate chart around Q.
You're varying the metric, right, during this gluing process?
Yeah, we're varying both the function and the metric.
Right. Otherwise, you can't glue a index 0 flow line at the end, right?
Sure. Yeah, so
Okay.
it's a homotopy of a function and the metric.
Okay.
That data is varying together. So yeah, we have some coordinate chart around Q on which this linear combination makes sense of beta minus u minus plus beta plus u plus. So this is our pre-gluing, and then now we can perturb. So far, we're like morally doing the same thing, you know, we did, just recapping what Joe did for us, except that, as Juan points out, we're varying the data. So we're going to choose these perturbations, C0 small, and we'll let U beta minus of U minus plus psi minus plus beta plus of U plus plus psi plus, where I'm mimicking Joe's laziness. Since he was lazy about this last week, I get to be as well. And like really there should be some coordinate chart, and I think we're all okay with this. So then we want to know sort of the conditions under which this glued thing is actually a flow line. Maybe we won't actually do the computations, which Joe showed to us last week, and I'll just say sort of by analogy. We're going to find that we have a flow line, so U actually satisfies this flow line equation if and only if, well, once again, we're going to have beta minus theta minus plus beta plus theta plus equals 0, where I need to define these thetas for you. So theta plus or minus, it takes in psi minus, psi plus, and t. So last week we didn't have this t. And then it spits out this questionable looking expression, most of which should be familiar from last week. And then I'll try to point out the slight. So these first two terms, they appeared last week when we didn't have this like t. It's these second two terms that look a little different. We didn't have the t del TV term at all last week. Quadratic terms depended only on the values in psi. They didn't depend on t at all. Oh, and I should make a little remark here that v is dependent on t. It's the gradient of f.
Wait, I thought V should come from the changing metric.
This term you're saying here should come from the changing metric?
Yeah.
Yeah, so maybe my naive way of thinking of it was, yeah, precisely what you're saying, but also V sub t of U plus psi plus. If you think about this term, it's just going to look like, I don't know, some sort of Taylor expansion where you're going to have this covariant derivative plus t del TV, and then plus some quadratic terms that depend on both t and psi. And this covariant derivative is going to get baked into the operator up here. But
Okay.
we'll have a t del TV that survives.
I see.
That's my naive way of thinking of it. But yeah, you're correct that it's coming from the fact that all this data is varying. Okay, so yeah, the setup is really the same. The structure is the same in that we have this equation, this beta minus theta minus plus beta plus theta plus. It's just that our thetas now look different. Yeah, so the punchline of Joe's story was that we could make these things vanish. So we have this obstruction up here to gluing, and last week, once you have chosen your R, you could then find psi plus or minus, plus and minus, is such that theta minus and theta plus both vanish. So we didn't really have an obstruction because the obstruction just always went away. There wasn't one. This week, we'll start obstructing gluing. So we have the next best thing. So here's our lemma. Once we've chosen R very large and T quite small, there exists a unique choice of psi minus, psi plus, each of these perpendicular to the relevant kernel, such that, well, we can get theta plus to vanish. And we can't get theta minus to vanish, but we can at least get it to live in an appropriate co-kernel. So it'll be perpendicular to the image of du minus. So I think I'll prove this at the same level of detail as last week's proof, basically by saying, look at last week's proof, because this is just going to be another contraction mapping. So we have these projections, pi plus or minus, from the L2 space down to the image. And last week we were able, because these map u plus or minus inverse, sorry, because du plus or minus was surjective, we were able to just define an inverse entirely and define it on the image. And instead of asking that theta minus and theta plus vanish, we ask theta plus to vanish and for pi minus of theta minus to vanish. Well, this is going to be equivalent to psi plus being this sort of unappetizing expression that I'll write out. Maybe I should have written this part out ahead of time. I apologize. So we want psi plus. This just comes from solving that theta plus we had earlier, set equal to 0. And then we'll have psi minus equals something very similar. We just have to put a pi minus on it. And then, just like last week, by choosing R sufficiently large, we can make this a contraction map, or a contraction. And then just apply the contraction mapping principle. So as last week, except that we have to sort of project out the theta minus direction if we want to solve it. So we still have this theta minus surviving, where theta plus. So we have an obstruction.
Sir, can I ask, but in particular, last week is a special case of this?
Last week, I guess yes is a special case, and it's special because we can sort of get this to be a contraction without having to do the projection theta minus. I'm a little...
I guess the question is, if you have transversality, then the image is the whole thing?
Oh, of course, yes, you're right, thank you. Yeah, being perpendicular to the whole thing, we would just get 0. You're right. So we can derive last week's lemma from this one. Thank you.
And this holds in a more general setup than the concrete non-transverse one that we're thinking, like the image could be higher codimension.
Exactly.
Would
Yeah.
be true. Okay, thanks.
Oh, thank you for making the point that I should have made. All right, so the upshot is that in any case, theta minus is going to be our obstruction. If it vanishes, then we can glue, and if it doesn't, then we can't. So now we can draw a picture, which I'm given to believe is quite important. So I'm not sure why they left it for me to draw, but I will. And hopefully it's helpful. So we can now build our obstruction bundle. And the base of this obstruction bundle will be sort of the moduli space of configurations we want to glue. And the fiber will just be this co-kernel where our obstruction lives. So we're going to have an obstruction bundle living over M, and I'll label these. And the fiber is just the space where the obstruction lives. So then we have an obstruction section, which, so that is supposed to be a math frac S. I'm not sure how successful I was in drawing it. I can guarantee that I will not be successful in continuing to draw it. So eventually that will just turn into a standard looking S, and hopefully it doesn't get confused with our parameter for our flow line. So the idea of this picture is that the set of gluings should then just be equal to, oh, it already turned into an S. Should just be equal to the intersection of our section with the zero section.
Can you say what the configurations to be glued are?
Absolutely.
And where the gluing parameter actually enters this picture?
Yeah, so in our case, so I tried to draw this picture somewhat generally because we'll need it throughout the semester. But in our case, M is just going to be this choice of R and T. The bundle will be trivial because we're not varying U minus.
The statement that the gluings, sorry, so the statement that the gluings are one correspondence with the zeros of the obstruction section, you're using some sort of uniqueness of your psi plus minus, right? I mean, you want to say something like, for sufficiently large R, you have this 1-1 correspondence. Correct?
Exactly, right. Because in particular, S sort of eats in R and T, but then it's going to spit out just this theta minus of psi minus psi plus T. So it matters that we can uniquely, that we get a unique pair psi minus psi plus for our choice of R and T. So there were two questions there. Does this answer both of them about what is M and why is this statement true?
I guess, I mean, in principle, you can just sum stuff in order to get the same equation, but the uniqueness of your psi's would prevent that, I guess.
You could just...
Like, you know, your equation, when you write down theta plus minus with, you know, the linear combination equal to 0,
Mm-hmm.
It seems to me that, I mean, in principle, you use the uniqueness of psi plus minus strongly to say this. That's all I'm trying to say.
Yes, and I agree. Okay, so in theory, at this point, we could figure out what all the gluings are by computing the zero set of this section. That sounds difficult. What we're going to do is we're going to have this linearized section on the other side.
Wait, sorry, I'm confused. R is your gluing parameter. So you're saying that for each value of t, which controls how the metric deforms, there's a unique or at least a discrete set of gluing parameters that will give you a gluing, right?
You're choosing both R and T.
Right, but if you think about the homotopy picture, like near t equals 0, you're varying t, and you're saying for each value of t, there's a unique or a discrete set of, okay.
So what we hope to say eventually is, like, given this value of t, does there or does there not exist a value R so that we can actually glue?
Okay, thank you.
And that answer is going to depend on the value of t. And it's going to be sort of an easy conclusion once we get there. But what we'll do now is compute a linearized section, S0, and then the idea is that computing the zero section of that should be good enough. And maybe the details of why that's good enough, I'm convinced just by the fact that it gives us a nice picture. I don't know if that's going to convince everyone here, but thankfully we have experts who can do some better convincing than can I. But the strategy now is to begin trying to linearize our obstruction section so that we could actually try to, given some value of t, maybe solve for R or something like that. So if there are no more.
Yeah, can I ask another question? So if this obstruction is not 0, you can't glue.
Correct.
But when could you possibly not glue? Like, does this happen for R-valued Morse theory that you can't glue?
Yes, this will happen in the donut picture from earlier. We'll find that on one side, when the donut is straight up and down, and on one side you can glue, and on the other side you cannot.
Okay. Thanks.
Sure. So what we need to talk about now is approximating the obstruction section. So let's see. We're going to have some projection down to the co-kernel of du minus. I said that the obstruction was just theta minus, but it's really going to be obtained by projecting theta minus to the co-kernel of du minus. So we're going to have this projection map. And we want to see what things survive projection and what things survive linearization. So I'll rewrite theta minus since it's sort of long gone up the screen. So we want to know which parts of this theta minus expression survived. So they need to survive A, projection, and B, linear. So two of these terms will just sort of immediately die. Certainly the first term dies when we project. And this quadratic term does not survive a linearization. Okay, so we can already say that this projection to the co-kernel that we're interested in is approximately just the projection to the co-kernel of the two remaining terms. So I think those two terms were without controversy, deleting them. Now I get to start making you angry, probably. I don't know, we'll see. The next term I want to delete is this psi minus.
Sorry, before you go on, can I ask a question?
Sure.
So this quadratic term presumably is quadratic on the psi's, right? So when you linearize, you're linearizing with respect to the psi's then, and setting them to 0? Is this what the S0 section does?
I don't know if I want to say I'm just setting them to be 0.
So then why is this, why did they die then?
No, you're right, I am. I guess I was just thinking quadratic terms are going to die in linearization, but I want to keep around my degree 1 terms in linearization, right? So I've confused myself now. I was just satisfied with quadratic terms don't to linear. It's sort of a first order approximation, right? So it's a linearization down the size, yes, but it's not as simple as setting them to 0. It's taking like a first order approximation in the size, right?
Okay, I mean, I guess that makes sense.
We're going to keep
I mean,
around.
I guess the S0 just keeps the linear terms and then just forgets about the quadratic ones. I guess
Yeah,
that's
yes.
okay.
However, I want to claim that the psi plus is not going to make a contribution to this term here, just because psi, maybe the way I want to say this is psi plus can only contribute when ds beta plus is non-zero. And if ds beta plus is non-zero, then ds beta minus is 0, just by the way we defined these cutoff terms. And because we know that theta plus vanishes, we find that whenever ds beta minus is 0, the theta plus actually has to decay. And so it's going to have some negligible effect on our projection here. And that should be a plus.
Wait,
So-
but U also decays, right? You have to say it decays faster than
U also decays, you're saying?
U plus, right? It decays to the Rabe orbit.
So we don't have any Rabe orbits since we're not doing ECH just yet. But
Oh, I see. Yeah, sorry.
so we'll deal with like the asymptotics of U plus shortly. But I basically just want to say the contribution of psi plus is negligible. I hope I spelled that correctly, when ds beta minus is 0. I will say this is the term I felt most unsure about throwing out, but this
Can I
moderate.
Can I ask another question before it goes off the top of the screen?
Sure.
I'm trying to imagine what the rigorous meaning of that squiggly equal sign might be.
Linearization. So linearizing in the size. Or maybe that's not a satisfactory answer.
So linearization, okay, linearization with respect to the psi, you're saying.
Yes. We have something in chat.
In the sense that this is a better and better approximation in the limit where the psi's become small.
Right. And Ipsita, next week's speaker, makes the important point that she says this is not actually a linearization, but just an approximation that behaves like one. Ipsita, if you want to comment, I'm happy to let you. And
yeah, I think this threw me off. Like, it's not actually a linearization. It just has the same number of zeros. So you're like taking all the significant terms, whatever that might mean. You're just making sure you're not losing any, like, you're not losing some zeros. I think Hutchings says towards the ends of the manifold, like as R goes.
So this fact about the zeros is something that I know from having heard countless talks by Michael about it, but I don't have any intuition for why that's true.
Sorry, so going even further back, there's a squiggle between what? Between two maps? You're saying two maps are close to each other? Or two vectors, or?
oh yeah, that's a fair complaint there. So we're thinking of this as some element in this coordinate chart, right? So I guess we can think of them as vectors if we like. But as far as the intuition as to why this approximation does not change the count of zeros, I am not going to be able to give a good intuition for that. Thankfully, I believe Michael Hutchings is here. He was earlier at least, and perhaps can offer some justification that I can't.
Okay, so my estimation of what's going on here is that, so if I just have like a polynomial on the real line and it has like a plus bx plus cx squared, then I guess if the coefficients look a certain way, I can count the zeros like near x equals 0 by just throwing out the square term, right? And that's kind of like what we're doing here.
Yeah, that's a fair assessment, I think.
Yeah,
so Michael chimed in the chat.
It's supposed to be like a Newton's method type solution, so either should apply in that context, right?
And this sounds like some form of what Michael's saying in the chat, which is that the motivation for the linearized section is that it should at least be plausible that it would approximate the actual section. But it doesn't need to be close to the actual section everywhere. You just need something like that on the boundary of the base space of the obstruction bundle, so that the zeros don't escape when you deform the linearized section to the actual section. So we need something that, for some fixed value of t, is still going to count things correctly.
Here, can I just ask the question? Can you hear me? This base space of the obstruction bundle is like a finite dimensional manifold, like R2 in this case, just
right.
R and T parameter. And so are we linearizing this section, like just a section on a finite dimensional manifold, or is it something, like that's what I thought it was, but now I'm all confused, so I'm not sure. That's the end of my question.
Thought it was as well, and I'm starting to get confused. So, Michael's answering. So there was another question from Yuan about the compactness of the base space. And Michael says that in these gluing problems, the base space usually has some boundary and is compact. I guess I did not think carefully enough about this and just wanted to say, if t is some very small number close to 0, can I or can I not find a value r? And I didn't think carefully enough about the compactness of the base space. I believe that was Dylan asking the question a moment ago, and I believe you have the correct understanding that we are this section over R2. It's just the word linearization here, I guess, Ipsido would claim is a misnomer.
This is really a question for Michael, I guess. Saying the base space is compact, I guess, assumes that you're allowing R equals infinity as a gluing parameter in some sense.
So
I'll try to talk. My internet's not very good, but like when you're gluing the like there's some range in which R can possibly lie if you fix T. So you sort of cap this off into an interval, and then you just want to count the number of zeros of the obstruction section on this interval, and then to show that the number of zeros is the same for the linearized section, you just have to check that on the endpoints of that interval, the linearized section is close to the obstruction section, or the difference between them is smaller than either of the two.
So you're saying that for a given T, you have some way of bounding how large R could be for a gluing to happen?
Yeah, you have to do something like that.
I don't see why that should be true. I mean, at the end, after you've somehow counted the zeros of the section, then you see it, but how do you see it before that?
Well, I guess this situation is a little different than the one I'm familiar with from my papers with TOBS. So my papers with TOBS, we definitely had like a limit. We were gluing branch covers, and there was definitely a limited interval of where the branch points could be. In this situation, I guess a priori, R could be infinity, or you could try to give some argument that there's a bound on it. I'm not sure what the best way to say it is. If you like, think of it as a interval going to infinity with infinity. Well, I mean, you would argue that the obstruction section is non-zero as R gets close to infinity, and that the same is true for the linearized section.
Yeah, I mean, I think that the fundamental point probably needs to be that the linearized section is as close as you want it to be to the original section when R is arbitrarily large, so that actually prevents this phenomenon of zeros escaping to infinity when you deform one to the other.
Right.
So that makes sense to me.
So in some sense, you're counting a relative C1 or something like this, rather than an actual count. Yeah. Right. Okay.
Yeah, it's like a relative Euler class relative to some boundary behavior.
if we're all sort of okay with approximation for now, maybe I'll just carry on and pretend that I know what I'm talking about. So at this point, we've reduced our approximation. We've got pi to co-cur of theta minus. I will once again use this nebulae and say it's going to be pi to co-cur of ds beta plus times u plus e, where I'm going to choose the projection so that it sends dtv to 1. So we need to investigate this U plus near Q. And I had sort of written down some details of this. I think maybe for the sake of time, I will try to just intimidate you into believing that near Q, before translation, in the S direction, we can write U plus as, let's see, e to the lambda minus s times eta, where lambda minus is eigenvalue of the Hessian of f at q, and eta is an eigenvector with eigenvalue lambda minus, and it's going to be determined by the asymptotics of u plus. So this expression is supposed to make sense in our coordinate chart that we chose earlier. And basically what we would do is sort of take some like eigenbasis for the Hessian at q, expand u plus in terms of these vectors. Anything with a negative eigenvalue is going to have 0 coefficient because, well, so actually we have to solve the differential equation. We get these exponential looking terms. Anything with a negative eigenvalue is going to have to die because when s goes to negative infinity, u plus needs to vanish. And then when s is very, very negative, we're going to find that, so this approximation is for s very, very negative, so that the exponential terms with larger positive eigenvalue are sort of negligible in comparison.
Just one question. Why do you know that when you project partial t of v to the co-kernel, that's non-vanishing?
I believe this is some sort of genericity assumption.
Generic is a one-parameter family of data?
Right.
Okay.
Yeah, so I think intuitively I would expect that to follow from the same argument that allows you to assume the co-kernel is only one-dimensional.
Right. Okay, so this is before translating. After translating in the s direction, u plus of s is approximately e to the lambda minus of, becomes s minus r over 2 eta. So when s is 0, which is what we have near q, u plus is approximately e to the negative lambda minus r over 2 times eta. And to assume that eta is non-vanishing. This is another genericity assumption. So ipsita, you're correct. It would be a linear combination of eigenvectors, but they would all have this eigenvalue lambda minus. And so it would still be an eigenvector of eigenvalue lambda minus. So if you use the argument from before about expanding an eigenbasis, yeah, you're going to get some linear combo, but they all have the same eigenvalue, so it's okay. Okay, so another statement that might make some of us angry is this projection up to rescaling eta is approximately e to the negative lambda minus times r over 2 times eta. So this derivative just vanished. My understanding of that, so this was what was in the notes, and my understanding of it is that this is a positive number, so we can just sort of rescale it into eta. All right, so altogether, if we sort of plug this approximation into here,
Wait,
we find
it's a positive number of size 1 over r. You're going to have some trouble with rescaling. Or maybe you won't, I don't know.
I'm just rescaling the vector here.
Right, by a factor that goes to infinity, or
I see what you're saying. Except that this 1 over r approximation for the derivative, that only holds for r large, right? Like this is, I'm sorry, for s large. And now we have s near 0.
okay, I'll think about that.
In any case, our linearized section that we're going to take, the function of r and t, r over 2 eta minus t, where eta is, by this genericity assumption, some non-negative number. I'm sorry, some non-zero number, perhaps negative or positive. So the conclusion, because we want to know whether we can solve this or not, or set this equal to 0 or not, we can glue, and in fact glue uniquely, if and only if eta and t have the same sign. Because if eta and t have the same sign, then once we've chosen t, we can solve this for some unique value of r. So what this means is we can glue on one side of t equals 0, but not the other. And so this relies on this like key fact that for some fixed value of t, the linearized section counts the zeros appropriately. It's going to count the zeros of the actual section, and that the actual is, generically transverse to the zero section, smooth. It relies on some facts that I've conveniently swept under the rug for this sort of toy calculation. But that's the punchline, is that we can glue when we tilt one way but not the other. I had some more pictures of donuts to try to think about the fact that we had 8 broken flow lines on the upright donut. 4 of them are going to glue when we tilt one way. The other 4 will glue when we tilt the other way. We'll stop with this conclusion.
Is there any way in this toy example to see somehow that this linearized section has the same number of zeros as the original one? I mean, retracing all those approximations that you've done?
I mean, it sounds like you're suggesting these approximations weren't thoroughly and rigorously convincing, which just shocks me. But it sounds like you're saying, yeah, can we do this in a more rigorous way? And the answer is, I don't know. I trust Michael Hutchings, but I maybe didn't check this quite as carefully as would meet your standards.
I mean, I'm not saying that it wasn't rigorous, but
no, I was just being somewhat silly. I took this not as something we actually wanted to know, but with a more nefarious goal of introducing us to obstruction bundle gluing problems. Perhaps since this is the one that might be tractable for me, I should have actually tried to do it carefully. But I took it more as an inspiring story than anything else. As far as whether the details can be checked, I don't have a good answer to that question.
I think it helps to kind of imagine, if you do a linear deformation between the original section and the linearized section, and just imagine what could possibly happen to the zeros as they move around, right? The key point is you have to know that they won't escape to infinity. And I think that's what this linearized section is designed to do for you.
I would also remark that for this this conclusion in this Morse theory case, you can check it by sort of finite dimensional topology. Like you can draw pictures of how stable and unstable manifolds intersect, and see that the like a co-kernel section in there and so on. I was discussing this with Ipsita at some point. So if you're skeptical, you can check directly that this, what you said about the signs is correct.
Well, just another thing. If you look at we said earlier that this is some kind of relative zeros we're counting. If you just look at what happens as r goes to infinity, which is at the boundary of one side of the boundary of this this space, you can see that everything else except the t term goes to 0, I think. At least for the linearized section. Maybe it's also true for the non-linearized section. So you could say, well, they don't have zeros in that way. Just some thoughts.
You're saying as r goes to infinity, the linearized section is just left with this minus t?
Yeah. And I think the unlinearized section will, most of the terms will also drop out.
Ah, okay, yes. Okay. So the conclusion was where I was going to leave it. But if there are any other questions, I'm happy to pass them along to people who actually know what they're saying.
Okay, so let's thank Austin, and we'll clap, and then I'll pause the recording and we can have our questions.